Okay, so let's move on to what the chapter is really about, the characteristic equation. The important thing is right here. The scalar equation, determinant a minus lambda I equals 0 is called the characteristic equation of A. I'll read the formal definition. A scalar lambda is an eigenvalue of an m by n matrix A if and only if lambda satisfies the characteristic equation determinant of A minus lambda I equals 0. So what this wants you to do, find the characteristic equation. Okay, so we do this from the definition, determinant A minus lambda I equals 0. So what do? We find determinant A minus lambda I equals the determinant. I told you that because this lambda I multiplication just results in an identity matrix with a diagonal of lambdas, all you really need to do is, look, you have 5, 3, 5, 1, right? You don't need to change anything else. All you need to change is 5 minus lambda, 3 minus lambda, 5 minus lambda, and 1 minus lambda, okay? And this shortcut, well, really it isn't a shortcut. It comes from a definition, but this, I'll say, trick works for anytime you see this A minus lambda I, okay? So you find the determinant, and it's this expression right here. You see that this 5 minus lambda occurs twice, and all the other terms occur only once, and the highest occurring term is what we call multiplicity, okay? So for this right here, this characteristic equation, it has a multiplicity of 2. And furthermore, you can, okay, what they're doing right here is just putting the lambda first and then expanding. So, oh, this is important. So now we know what multiplicity is, okay? It is the term with the highest number of occurrence, or I could say the leading term raised to some leading power, okay? That's what the multiplicity is. And this sentence right here is actually important. It can be shown that if A is an m by n matrix, then the determinant A minus lambda I is a polynomial of degree n, called the characteristic polynomial of A, okay? So, it's a polynomial of degree n. So look at this. This is a 4 by 4 matrix, right? 1, 2, 3, 4. 1, 2, 3, 4. N by n, 4 by 4, okay? So because n equals 4, you have 4 terms, okay? That's all this sentence is saying right here. What they want you to do is, right here, they give you the characteristic equation, find the eigenvalues and their multiplicity. So what you do is you first factor this lambda to the 4th outside of the expression. Then you factor this inner quadratic expression, not an equation, and this is what you get. So the eigenvalues are right here. This is lambda. Lambda to the 4th is really lambda plus 0. So you have the eigenvalue 0 with a multiplicity of 4. The eigenvalue of is 6, yeah, to the multiplicity of 1, and minus 2 to the multiplicity of 1. Because this is lambda plus 2, right? What this really is, you have to remember that right here, all of these are lambda minus something, okay? What we really have is lambda minus 2 here to get lambda plus 2, okay? That's why you get minus 2. And right here, you have lambda minus 6. The 6 is without the sign, so that's why it goes right here, okay? If that was unclear, by the way, send me a comment below in this video and I'll answer it right away. So now we come to the concept of similarity. So let me read this. A is similar to B if there is an invertible matrix P such that the inverse of P times A times P equals B, or equivalently A equals P B times P inverse, okay? So that's just the definition. As confusing as it sounds, you have some matrix that satisfies this equation, which by default makes it also satisfy this equation right here. So now that we know that this works, if you substitute this Q for this P inverse, then we have this Q inverse BQ equals A. So just as we proved that A is similar to B, we also proved that B is similar to A. Therefore, when we prove them both ways, we can say that A and B are just similar, okay? We don't have to say A is similar to B or B is similar to A. They're just similar to each other. And you see right here, hold on, I'm sorry. Changing A into P inverse AP is called a similarity transformation. Okay, yeah. So what they're saying is this expression right here is also in linear algebra jargon called a similarity transformation, okay? That's not important. Theorem 4. If n by n matrices A and B are similar, then they have the same characteristic polynomial, okay? And hence the same eigenvalues with the same multiplicity. Fair enough? And then they have this warning right here. The matrices 2, 1, 0, 2 and 1, 0, 0, 1 are not similar even though they have the same eigenvalues. Similarity is not the same as row equivalence. Row operations on a matrix usually change its eigenvalues, okay? This warning is important, so reread this, but really I think you need to know this definition and this theory right here, okay? And this understanding will come naturally. Thank you very much. I'm going to stop this video.